All right, let's look at some examples of how exponential functions are used. We're going to do two of them. If you need to pause the video at any time, go ahead and write this down. But here is problem number one. In 1981, the humpback whale population was 350. They were very endangered. But they have increased at a rate of 14% each year since 1981. Letter A, write a function to model the population growth. All right, big key, percentage. Percentage usually indicates exponential problem. Now, from the last video, you learned that the formula for an exponential problem is y equals ab to the x power. I'm going to go one step further with that formula. I'm going to write it like this. Y equals a, and the b part I'm going to write as 1 plus or minus r to the x power. Anytime you have a percent problem, the r is the percentage. R is the percent, obviously written as a decimal. Now, if I change 14% to a decimal, I get 0.14, which is my R value in that formula. So, I can write my function for population growth. Y equals, well, A, I said on the last video, is the start point. The population starts at 350. Now, in the parentheses, since it's increasing, that means my number's got to be bigger than 1 since it's increasing. It's got to be this is a growth problem, people. It's growing. So 1 plus 0.14 to the x power, which is the same as 350 times 1.14 to the x. That's what you're going to type in your graphing calculator, what I put in the blue circle. That is the function to model this growth. Now we're going to use it to make some predictions. It says in letter B, use the graph to predict when the population will be over 20,000. All right, so I'm going to do a little bit of erasing here. I'm going to erase that growth. We understand it's a growth problem. I'm going to make a t-table here. X, Y. All right, X is my time period. So year 0 is 1981. And it says in year 0, our population was about 350. All right, now, if you use your graphing calculator to help you with this problem, you will find out by going to your table, if you type this in. Now I'm going up by increments of 5. After 5 years, our population is about 673. After 10 years, it's about 1,297. After 15 years, it's 2,498 roughly. After 20 years, it's 4,810. After 25 years, it's 9,261. I'm going to do a little bit of erasing here. After 30 years, it's going to be 17,833. Now, if I was to graph these, and I'm going to change my numbers on my scale, what I'm going to do is I'm going to delete this and draw my own graph. All right, and we're going to label it 0, 5, 10, 15, 20, 25, 30, and out here would be 35. It's going off my board. And then going up, we're going to go up by 1,000, or actually we're going to go up by like 5,000. So here's 5,000, 10,000, 15,000, 20,000, 25,000, 30,000. And that's what I'm going to put in a little arrow here. It's in thousands. All right. So if I plot my numbers at 0 in 1981, year 0, there was about 350. That's way down here. After 5 years, it was 673. That's still way down here. Because remember, these numbers over here are in thousands. Year 10, we're finally at 1,000, which is about right there. Year 15, again, I'm estimating people. Year 15 is about 2,000. It's about right there. Year 20 is getting close to 5,000, which is about right there. Year 25 is about 9,000, which is going to be about right there. Year 30 is 17,000, which is going to be about right here. Now, as you can see, we're forming an exponential model. It's going to keep going up like this because this is a growth problem. So the question is, use your graph to predict. Obviously, it's not going to be extremely accurate, but when the population would be 20,000. Now, 20,000 is in here, and if I go over to my line and down, oops, that didn't turn out straight, but if I go over to my line and down, if I can do this, it's hard on this board since we're going off the edge, but if you do it right, the year is around year 31 when the population finally gets to 20,000. If you got questions about this example, please ask, but that's how you do it, and that's where exponential growth and equations comes in. Example 2. A new softball dropped from a height of 25 inches rebounds to 2/5 of its original height. The question, write a function to model this decay problem. Now, the key is this is going to be decay. The reason it's decay is because it only rebounds to 2/5 of its previous height. Well, from the last slide, you saw that our formula is like that. Now, since we are only going to 2/5 of its previous height, that is 40%. Now, actually, this is actually our B value. It's not a percentage, so we don't need to use that. All we got to use is AB to the x power, since it's not a percentage. So therefore, our original starting height is 25. Our B value is 2/5. Now I'm going to change that to a decimal. That's 0.4 to the x power. And there you go. There is your function for this decay problem. And it's decay because that number is less than 1. All right. So now I'm going to make a table here. And I'm going to change these numbers to end in 0. 20, 40, 60, 80, 100. Now, if you type this equation in your graphing calculator, at 0, the ball is 25 inches high. So 25 is going to be right there. The first bounce, it bounces only 40% as high. So it only bounces to 10. So on the first bounce, it rebounds to 10. On the second bounce, it only rebounds to 4. Again, I'm using my graphing calculator to look at my table and do this. On the third bounce, it says it's 1.6 inches high. Well, that's going to be about right there. And as you can see, our graph is modeling a decay problem. Now, technically, will the ball ever stop bouncing? The answer is no. It really technically never stops bouncing, but it always gets closer and closer. The y value is getting closer and closer to 0. Well, use the graph to predict when it will bounce less than 1 inch. Well, the answer is going to be 4 because it's way smaller. At 4, it says it's 0.64. So the answer to our question is on the fourth bounce. That is when it will not come up to 1 inch high. That's how you do a growth problem, and that's how you do a decay problem. That's pretty much what we're going to be doing this entire unit.